I turned on. Okay, thank you very much. Thank you for the invitation to speak here and for organising the summer school. I'm delighted to be here in Taipei. So today and tomorrow I'm going to give some lectures on pattern classification, theoretical results in pattern classification. So let me start by giving you the overview of the 2 days lectures. I want to begin with, in this lecture, with a formalization of the pattern classification problem. So can everybody hear me? Is this? Yeah? Great. With a formalization of the pattern classification problem and some examples of the types of classes of functions that we're dealing with, which we'll be reviewing, some of the things that you've seen. I want to make sure we do fix the notation. And then I'll look at a general way of obtaining risk bounds, so performance guarantees for pattern classification methods, using something called Rademacher averages. So that'll be in this lecture. In the next lecture, we'll look at some aspects of the VC theory, Vapnik-Chervonenkis theory. And we'll get on to we'll get on to properties of large margin classifiers tomorrow. Okay, so let me start by looking at the pattern classification problem and defining the problem. So here I'm considering, we'll assume always that we have IID data. So we have a probability distribution P, and this XY pair is distributed according to P. It's a distribution on the product space. X here is some domain. This is the space of possible patterns that we can see. Y is the space of labels. And we're assuming that the cardinality of Y is finite. All right? We're wanting to classify elements of X into one of this many classes. And for most of what I'll talk about over the next 2 days, the cardinality of Y is going to be just 2. Right? We'll be looking at the 2-class case. So we assume that we see n XY pairs, right, that have the same distribution. They're independent, and there's that's the same distribution as that of XY. And the aim here is to use this training data, these n XY pairs, to choose a decision rule that is a function that maps from X to Y, so that the risk of that function is small. The risk here is the expectation of the loss. Right? So we define some loss function L, which tells us how bad it is to make the prediction f of x when the true outcome is y. Am I?
Yes. This is for recurrent purpose.
Okay. Is this better? So our loss function L measures how bad it is to make a prediction f of x when the true outcome is y. All right, so we're interested in the expectation of the loss expectation under this random choice of the xy pair. Right, it's distributed according to P. Okay, we'll call this the risk. And for instance, the case that we're typically concerned with here in the binary classification case in particular, this loss function would be the discrete loss, the 0-1 loss. Right? We incur a loss of 1 when our prediction y hat is different from the true outcome y. Okay, so some examples. The space of patterns X might be a mass spectrogram. The class Y represents different disease states, and we're wanting to use this mass spec data from somebody's blood serum to decide whether they've got prostate cancer. Okay? So, I'm thinking quite abstractly. The domain here is not necessarily, a Euclidean space, although many of the examples, for many of the examples, we define some set of features on this space and then look at a Euclidean a representation in a Euclidean space. Another example, character recognition. So this domain X might be features of some handwritten character, and the space of labels Y is how we want to classify these characters, right? The set of possible characters. Or X might be some properties of the 3D structure of a candidate drug molecule, and Y represents properties of some property of interest. All right, so whether that molecule has some acceptable pharmacological property like receptor binding affinity or something. Okay, so the key issues in pattern classifications of problems of this kind are issues of approximation, estimation, and computation. So the perspective here is we're thinking of F as being chosen from some fixed class, capital F, right? Some fixed class of functions. And then having made that restriction, all right, we have an approximation question of how well can functions in the class F solve this pattern classification problem. That is, what's the smallest value over all functions in F of the risk, the expectation of the loss incurred when we predict f of s and the outcome, f of x and the outcome is y. I might have flipped the arguments from my earlier definition here. All right, so the approximation, this is a property of our class of functions and the underlying probability distribution on x by y. Estimation is this statistical issue that we only get to choose our f, or let's call the estimator f hat, right, using a finite sample. Okay, and so the expectation of the loss might be rather far from the best that we can do in that class, right, because the only information we have comes from a finite sample. And of course, the computation issue, we're concerned that we can use the training data to choose a suitable f efficiently. So these are the three things that we're going to be concerned with. So in these talks, I'm not going to focus at all on the approximation question. I'm going to be looking mainly at the estimation question and to some extent at the computation question. All right, so let me say a little bit about the classes of functions f and the pattern classification algorithms that, just to give some examples of these, there are things here that you've seen in some detail already, and things you'll see in some detail in these talks. But as I say, I'd like to make sure we're all clear on the notation that I'm using when we see these as examples later. Okay, so let's think about the class of linear threshold functions. Right here we're thinking of a Euclidean space, so our domain X is just Rd, it's a d-dimensional, so there are d real inputs. Right, we're worrying about classification into just two classes. Okay, so from this point on, the set Y has cardinality 2. It's just, we'll call it plus or minus 1. The two labels plus or minus 1. And our class of functions here is the set of linear threshold functions. Okay, functions that map from X to the sign of W, the inner product between W and X for some weight vector W in Rd. Okay, so in 2 dimensions, all right, this is an example. The blue represents the plus one region, the decision region. Okay, in a classical algorithm for linear threshold functions, the perceptron algorithm involves updates to the parameters. All right, so we can think of that, and again, this is something that you've seen already. We can think of that in terms of the updates here involve only the linear combinations of the patterns xt. Okay, so we can represent our parameters either in terms of represent our function either in terms of these linear parameters or in terms of coefficients associated with each of the xt's. Okay, so Another example is a class computed by neural networks. So let's think about sigmoid networks. Here the domain X again is RD. The class of functions, these are functions that map from an element of RD to the sign of some linear combination of nonlinear functions of the inputs. Those nonlinear functions involve inner products passed through some scalar nonlinearity, this function sigma. All right, and this is typically a squashing function. So for instance, we might consider this kind of function that maps to the interval 0, 1, or some scaled version that maps to -1, 1. All right, so we have two types of parameters here. There are the ones that enter nonlinearly and the ones that enter linearly before we take the threshold. All right, so this is another class we might consider. The algorithms there typically work by minimizing, use heuristics to minimize some sort of a smooth criterion. All right, so for instance, we might worry about the sample average of the squared difference between the true label y and the value f of x, or the value f before we threshold. So this notation e hat here I'm using to okay, I've said that down there. Using to represent the expectation under the empirical distribution, right? The sample average of this quantity. Another example is decision trees. So here we could consider decision trees where we have, these can be represented using a tree. The nodes of the tree are decisions based on, correspond to decisions based on a single axis projection. So again, X is RD. All right, we're considering now, we can define these things recursively. We look at decision trees of depth 0 as ones that just map to some constant value, either plus or -1, right? And then decision trees of depth I plus 1 correspond to, take a decision tree of depth of two decision trees of depth I and use those to form our decisions, and then add a decision node to the top of that. So typically, the class of decisions computed by these nodes might be the class of threshold functions on one-dimensional projections, where we on single axis projections. This kind of a thing. All right, and the algorithms that are typically used here, again, they're heuristics to optimize some sort of an empirical criterion. And the standard approach is to grow the decision tree from the root, choosing a leaf of the tree to expand, and then adding in a decision node at that leaf so as to minimize some sort of an empirical criterion, some sort of an error criterion based on the training data. And there are various heuristics. I mean, it's common to grow a tree completely until the tree correctly classifies all of the data, and then prune the tree back according to some criterion, some empirical criterion again. Okay, and we'll be considering these as examples of basis classes, for instance, for methods that combine classifiers. Okay, so let's think about those voting methods. So here, our class of functions. These are functions that, again, they're thresholded linear combinations, but now not of the components of the vector x, but of functions defined on x, functions from some basis class G. Okay, so here we're taking, you can think of this as each ft is a member of our committee, right? Ft is some basis function, maybe it's a decision tree. And we're combining those FTs with some real valued weights, and then we're taking the weighted majority decision. Okay. Okay, so and an example that we'll consider later again is these G's are very small decision trees. So decision trees of depth 1. These are also called decision stumps. Okay, so the class here is these are just functions that map to two values depending on some linear threshold function on a single component of the input vector. All right, and one class of algorithms for working with this class of functions are the boosting algorithms that maintain some sort of a probability distribution over the data and choose the basis functions in order, in some sequential order at each step, minimizing some sort of an empirical criterion. And typically this can be expressed just in terms of this weighting function as weighted empirical error. And the intuition here is that we're adjusting the distribution over the data so as to emphasize the mistakes that our committee, our previous combination, has made on the data. Okay, and I guess I don't need to spell out the particular approach taken with AdaBoost here. Well, let me just say that AdaBoost is one approach here where the weighting is chosen so as to the choice of the weighting corresponds to choosing a function f from the linear span of our basis class so as to minimize the sample average of some exponentially decreasing function of y times f of x. Okay, so just intuitively, you know, f of x is this real valued function here. Y takes values plus or minus 1. So, you know, it seems reasonable that we would be trying to find a small value of this criterion which corresponds to y times f of x being large and positive. Right, so that means f has the correct sign. Okay, and that's all I'll say for now about boosting algorithms. Kernel methods. Again, you've seen this. Here we've got a rather general domain, an input space X, on which we define an inner product and come up with a suitable inner product, I should say, and come up with a Hilbert space that is a reproducing kernel Hilbert space. And the class of functions that we're considering, we can view SVMs as working with a bounded subset of linear functions. All right, so we look at functions that compute just inner products, right? But the functions are bounded. The RKHS norm of the functions is bounded. Or equivalently, we can parameterize them by an element of our Hilbert space and think of the parameter W as having a bounded norm. And again, just as in the perceptron case, you know, the neat thing about this kind of approach is that even with a general inner product on a complicated space, we can always represent the function implicitly, you know, using this dual representation by recording just the weights associated with each, just a weight associated with each of the xi's in our training data. All right, and the approach that's used in the typical SVM is to, we consider that class of functions and we minimize some empirical criterion. All right, this is the sample average of a cost function, again involving y times f of x, plus a penalty term. So this is a regularization kind of approach. We have a regularized empirical criterion here. Right, and the cost function that we're concerned with, right, in this case is a piecewise linear function. It's the hinge loss. All right, so this was intended to give you an overview of the kinds of approaches that I want to consider, function classes and algorithms for pattern classification. And now let's get on to performance guarantees, so getting risk bounds for algorithms of this kind. So the general approach that I want to use here is Rademacher averages. I'll start by telling you a bit about the very idea of risk bounds, I guess, that we want to understand how we should control the complexity of the functions that we have so as to best trade off the competing issues, right, that we face, these approximation, in particular the approximation and estimation issues. I'm going to introduce some concentration inequalities that tell us how sample averages converge to expectations and how concentrated these things are. I guess a bit more generally than just sample averages. We're looking at concentration of other of more general random variables about their expectation. And then we'll be using these ideas in proving risk bounds using a measure of complexity called Rademacher averages. So we'll get onto those in a moment. Okay, but just first a bit of intuition. So if we think of this, the framework as I've outlined it, we have a class of functions, capital F, and we'd like to choose some function from that class so as to minimize the expectation of the loss or minimize the risk. But we have these competing issues. If we were to choose a function from a more complex class, then we're going to do better in terms of the approximation properties, right? The infimum over the class, the minimum over the class of the risk for a bigger class is something that will be smaller, but will suffer on the estimation side, right? A more complex class, we only have information about the class presented to us in the form of this finite set of labeled examples. Okay, so the key issue here is trading off these two properties, the approximation properties and the estimation properties. So coming up with estimates of the risk in terms of, for instance, the sample size and some measure of the complexity of F tells us how to control the complexity of F. For instance, using some method of sieves, some approach where we say for a given sample size we can work with a class that's this complex, and as the sample size grows we can choose some function from a bigger and bigger class. Or an approach that's very, very closely related is a regularization approach. For instance, introducing an extra parameter into an empirical criterion, such as the RKHS norm regularization parameter in the SVM. Okay, so these are two general approaches of controlling complexity. So let's think now about, suppose we have a case where we've got a very rich class, capital F, and we split it up into some hierarchy, right? So we're thinking of choosing functions from this class, but it's way too rich to estimate some function from that class near optimally using a finite sample. So we split it up. We come up with some hierarchy. We represent functions. We represent this class as a union of simpler classes, F1, F2, and so on, where for each k, what we're going to do is choose the best F sub k in the class capital Fk. Okay, and for instance, we might do that by minimizing empirical risk. And then we'll choose an Fk, right, one of these optimal guys, so as to minimize a complexity penalized empirical error. Okay, so this is a generic approach that we might take. You could think of this hierarchical representation, for instance, for things like decision trees. The index k might be the restriction on the number of decision nodes in the tree, or for a reproducing kernel Hilbert space, the index k might allow an increasing radius of a ball in an RKHS, right? F sub k would be a subset, a ball in the RKHS of radius rk, where rk is increasing with k. Right, and then we're thinking of, so here's one general approach. We're thinking of choosing some function from from this union so as to minimize a sample-based estimate of risk plus a penalty term involving the complexity of the kth class. Okay, I could have written this just as P sub k. Okay, so in the decision tree case, this would be a penalty that increases with the number of nodes in the decision tree. In the RKHS case, it's a penalty that increases with the radius of the ball in the decision tree. All right, so that's a kind of a method of sieves with a complexity penalty there. A regularization approach, we could again consider this rich class, but instead of doing an explicit partition into a union of classes, we could minimize directly over this class a complexity penalized empirical error. Right, so here we have, this is a sample average of, this is a sample-based estimate of risk, and here we have a penalty term that depends on the function f itself. Right, so this might be, for instance, in the RKHS example, this might be something involving the norm of, the RKHS norm of the function f. Well, that's not so different from the method of sieves on the previous slide, right? If we think about the decomposition now into the set of functions that have this complexity penalty smaller than some value, right? That defines, so now we can express f as a union of this kind, union of classes of this kind. Okay, so coming up with bounds on risk in terms of sample size and various notions of complexity of functions or function classes, tell us what is a suitable complexity penalty to introduce here, right? So how we should restrict f when we represent it as a union of these f sub k, or equivalently how we should regularize our functions. All right, so the key tool in obtaining these risk bounds that I'm going to be telling you about over the next couple of days are Rademacher averages. So this is an important definition, and it's going to be central to you know, what I have to say certainly for the rest of today. All right, so the Rademacher averages are defined in this way. So we use the notation R sub n of f. This is our function class, and this operator is defined as, so we have the supremum over the class of an average of these sigma i's times f of xi. All right, so this is a random variable. The sigma i's here are called Rademacher random variables. So these are IID uniform on plus minus 1. Okay, so we're looking here at an inner product between f, excuse me, the function f evaluated at each of the n points x1 through xn in our sample, right? An inner product between that vector of values and this random plus minus 1 vector, right, of the sigmas. So Rn of f is the supremum over all functions in our class of this inner product. So we're saying take a random vector sigma i. So first of all, let's fix the sample x1 through xn, right? Then take a random vector sigma 1 through sigma n of plus minus 1 values. Now look at how much each f in our class evaluated at x1 through xn, how much that lines up with this random vector. Okay, what's the biggest inner product we can find? As f ranges over the class, what's the biggest inner product we can find between f of x1 through f of xn and sigma 1 through sigma n? Okay? And this is the value of that biggest inner product. Okay, so it's a random variable. I guess there are there are two things in here. There's the sample x1 through xn, that's random, and there's the sigma 1 through sigma n, those are also random. Okay, so this thing is a random variable, and we're going to, in fact, we'll see this is tightly concentrated around its expectation, or any of the conditional expectations that we want to consider are tightly concentrated around their expectation. But let's think now just about removing that randomness. Let's consider the expectation of this thing. Well, that measures how well our class can correlate with a noise vector sigma. Right? So you're picking, the sigma is just some random direction, and then we're saying now try and find an f that lines up with that direction. Okay? It's not a uniformly chosen random direction, it's just on the vertices of the plus or minus 1 cube. In fact, we could define this thing not in terms of Rademacher averages, but in terms of, you know, Gaussians or elements of uniformly over the sphere, and, you know, all of the results that I tell you will change by, I guess, no more than a log factor anywhere, right? So you can think about this sigma as just being a random direction, right? And we're asking, so now how much can we line up with that random direction? If we can always line up, so for essentially all choices of this direction, we can come up with an f that has some nice big value of this inner product, right? Then that tells us that, you know, we're unlikely to be able to infer very much from the training data, right? Because we can get essentially any labels we want, any sign we want from our f of x. Okay? So that's a bad thing, right, from the statistical point of view. So one other thing I guess I should point out, this is a notion of complexity. So that's one way to think of it, right? We're measuring how complex our class is, but we're measuring that complexity with respect to the probability distribution that we see, the distribution that generates the x's, at least. So the marginal distribution on the x's. And it's also, of course, so it depends on the combination of the probability distribution and the function class f. Okay, so here's a theorem that gives us a bound on the risk of a function in some class in terms of sample averages or empirical risks. I'm going to express it not in terms of risks. I'm just saying, look, we've got some class of functions that take value in some bounded interval, and I want to know about expectations compared to sample averages. Okay, so the case to think of is these functions are loss functions, right? The loss incurred on a sequence of xy pairs. So the empirical loss, the sample average of the loss versus the expectation of the loss or the risk as we've defined it. Okay, that's the case to think of. So what's the result? We've got our class G of functions that take values in some interval. We can say with probability that gets close to 1, uniformly across this class. So for every function in the class, expectations are not much bigger than sample averages. Right? And how much bigger? Well, there's some small term that depends on, you know, how close we want this probability to be to 1, right, in terms of this number x. Okay, that's like a 1 over square root of n thing. That's small. And then we've got something that's the expectation of these Rademacher averages. Okay, and so when we think about this G as being the discrete loss that we incur for a particular class of plus minus 1 valued functions, all right, we can write the special case down here. You know, it turns out these two are related. We'll see in a moment. We can write that the risk so uniformly over the class f, the risk of a function f is no more than the sample average, or the empirical risk, plus some penalty term involving the complexity of the class, the Rademacher averages. Okay, so we'll have a look at this, at why this theorem is true. But first, let me point out a few things. Well, let me just reiterate. The Rademacher averages here are a property of both the class and the probability distribution, right? So we're capturing somehow how the probability distribution emphasizes or exercises the complexity of the class. Later we'll see that we can come up with estimates of this sort of a quantity in terms of distribution-independent notions of complexity like VC dimension and covering numbers and various other things. Okay, so let's say a little bit about the proof of this result.
I have a question on the
Yeah, great.
previous slide.
I can't see.
In your theorem, it says G over 0, 1.
Yes.
And the class is plus or minus 1. So
Right.
minus 1 is outside that, don't you?
Right. So here this class G is you should think of as the class of loss functions, right? So for every so G is defined as the set of, let's call the functions L sub f as f ranges over the class capital F, where L sub f is the loss function, the function that maps from an xy pair to the loss incurred when you predict f of x and the outcome is y. Okay, so these things are the plus or minus 1 valued functions we use to predict. These things are the losses that, and the domain here is x. These things are the losses that we incur, right, when we use a particular function to predict, and the domain is x cross y.
So the loss is between 0 and 1.
The loss is bounded between 0 and 1, that's right. And down here we're thinking of the special case where the function is... So okay, I guess I didn't say earlier, you know, the first part of the theorem here, you know, is more general than just the pattern classification kind of setting. But when we apply it, you know, we'll always be worrying about loss classes of this. Well, actually, that's not true for tomorrow, but for today, we'll always be worrying about loss classes for plus minus 1 valued functions. So yeah, this is the general result is for loss classes, and we're concerned about loss classes of plus minus 1 valued classes. Are there any other questions?
Yeah, on the previous slide, is the sigma fixed or research the whole space of 2 to the n cases?
No, the sigma I are IID uniform and plus minus 1. So they're random variables. So this thing is a random variable, right? It's a random variable because it depends on the random x1 through xn, and it depends on the random sigma 1 through sigma n. Okay, so we're not doing any optimization over sigma, we're doing an optimization over the function f.
So essentially you want that random variable to be very, very small. You don't want to be noisy.
This random variable, that's right.
You want to be correlated with whatever.
That's right. So if you think about, you know, throw that supremum away and think about a fixed f, right, then this thing has mean 0, right? Each sigma I has mean 0, and so the expectation without the sup is 0. Okay, so we're doing a maximization, so we'll always do at least as well as 0. So this random variable takes a value that's at least as big as 0. And the bigger it is, the more that we can find a function in our class to line up with a random vector. Okay, so the richer our class is. All right, and now when we look at how that appears in the theorem, the theorem tells us that if we've got a class of functions that take values in some bounded interval, then expectations are uniformly close to sample averages, provided that this notion of complexity is small, right? So if we are in the case where, you know, we're not doing much better than if we throw this supremum away and we have just a single function, this thing would be 0, right? If we have a much richer class than that and the supremum lets us line up really well, right, and this is a large value, then the theorem becomes weaker, right? We get a much bigger quantity here on the right-hand side. We can't guarantee that the expectation is not much bigger than the sample average. And I've written the inequality in one direction here. I mean, I could have put absolute values around the difference between the expectation and the sample average, right? I could. So, you know, the interval being 0, 1 is not really crucial. It could be any bounded interval, so I could consider negative functions, negative the set of negative g, where g comes from g, and get the same thing. So, I can get exactly the same inequality, but two-sided, I guess I'm saying. And I should say, in everything that I'm doing, I'm really relying on the fact that we have bounded random variables. We'll see later that this is crucial for the concentration inequalities that we need. I mean, I guess it could be relaxed if you know something about the tails of certain distributions that will appear, but I don't go into that at all. And in our case, for binary valued functions, in fact, for everything that we do, these tools are powerful enough. We can always work with bounded loss functions. Okay, so let's take a look at how this theorem is proved. What we're looking at here, I guess one crucial thing that maybe I should emphasize again, is that we're talking about a result that's uniform over the class. All right, so with high probability, right, every function in our class has expectation sample average close. Okay, and that means if we choose some function to minimize the empirical risk, right, minimize the sample average of the loss, then we know that the loss for that function, that minimizer, is going to be not too big. Okay, so it's a uniform convergence result. It tells us about the uniform deviations between expectations and sample averages. Okay, so what we're really concerned with here is saying, that the probability of the event that the maximum over this class of the difference between these two is big, that probability should be small. Okay, so we're interested in this quantity. Okay, the maximum over our class, G, of the difference between expectations and sample averages. Okay, and the concentration result that we use for that particular theorem is a general one that's called McDiarmid's inequality. It's also known as Hoeffdinger-Zuma, and there's another name that escapes me for the moment. But this is a result that I guess appeared in a paper of or something equivalent appeared in a paper of Hoeffding, a very long time ago. So this result is a concentration result for bounded random variables. It tells us that that if in particular we have a random variable such as this one that depends on x1 through xn. All right, so this thing is just the maximum over our class of the expectation minus sample averages. Okay, that's random because it's a function of the random variables x1 through xn through this sample average. Okay. Now, McDiarmid's inequality tells us that if we have a function of IID random variables, as we do here, right, then we get concentration of that random variable about its expectation, provided that no one of those independent random variables has a big influence. Okay, so how do we formalize that? So the random variable we're thinking of is this one, in our case. But let's think now about, so this thing is a function of x1 through xn. And the crucial condition that lets us apply McDiarmid's inequality is that when one of these independent random variables changes, the function that we have can't change by much. So how do we measure that? Well, the sample average of G is a function that takes values in the interval 0, 1, right? So the sample average can't change by any more than 1 over n. Okay, it might go from one extreme like 0 at a particular xi. G at xi might change from 0 to 1 if we change that xi. Okay, so the same thing must be true for the supremum. If we change one of the xi's, this thing can't change by more than 1 over n. And that means that this random variable is concentrated around its expectation. So precisely, the form of McDiarmid's inequality is that this random variable is not much bigger than its expectation plus a little bit. This little bit depends on the fluctuations that we see when we change one of those random variables. Okay, so this is a very general and nice and easy to apply inequality, right? We're talking about a random variable that can be expressed as a function of a bunch of independent random variables. If we change any one of those, does the function change by not too much? And if that's the case, then our random variable is concentrated around its expectation at this kind of at a level that depends on the size of the fluctuations. Okay, so that's at the heart of the proof. All right, so let me state this concentration inequality precisely. So we have n independent random variables. I'll call them x1 through xn. Now, and we have a function that maps from some domain x, maps from the space that these lie in to the reals. This is not true. This should be a bounded interval, and in fact, no, this is true. Okay, so it maps to the reals, and then we have that whenever we take any value of x1 through xn, and any other any I and any xi prime, okay, so maximizing over all of the arguments of our function. If we look at how our function g changes when we change xi to xi prime, right? The biggest change that we can get is ci. Okay, if we have this condition satisfied, this is the bounded differences condition. There's another name for this inequality, the one I forgot a moment ago, the bounded differences inequality. Then with high probability, the deviation between our random variable and its expectation is small. On the order of the 2 norm of this vector of these maximal deviations. Okay, so when we apply that in our case, our g has fluctuations that are of order 1 over n. Okay, so we get a sum of n terms of 1 over n squared, and we get our square root of x over n term down here. Okay. All right, so that's taking us a step in the right direction. We've gone away from, remember we're trying to show that expectations are not much bigger than sample averages. We uniformly across the class. We're trying to show that the supremum over functions g in our class of differences here is not too big, and what we've first shown is that random variable is not much bigger than its expectation. Okay?
So in this case, g in the McDermott inequality, there's no condition saying that g has to be bounded.
There's no condition saying that g has to be bounded. We have a...
in the other case, you have a case where g is bounded.
Right. So g is bounded here implicit... So the point is we're always looking at differences. Right, and for any change of these variables, we're getting a small change. So g is necessarily bounded because we're getting no more than a sum of these changes to, right? G is not necessarily bounded. If we subtract the value of g at some fixed value of x1 through xn, right? Then just centering g around 0. So for some value of x1 through xn, this thing is 0, then g is bounded by the sum of the ci's. Right? And the way that we use the boundedness of g, so I guess what's confusing here is that there are 2 different g's floating around. G means 2 different things on this slide and on this slide. Okay, so here we have a class of bounded functions. The fact that they're bounded, right, means that the sample average can't change by much when we change one of the arguments. Okay? The random variable we're considering to apply McDermott's inequality is the supremum over g of the expectation minus the sample average. So on this slide, in stating McDermott's inequality, I shouldn't have used g, right? I should have used some other symbol for the random variable, right? So the random variable we're talking about here is, in our case, this thing, right? So sorry if that was an unfortunate choice of notation here. Okay, so I want to say a little bit about why, about McDermott's inequality and why it's true. And some of the ingredients of the proof here will pop up later when we consider the VC dimension. Okay, so we're looking here at deviations between the function g of these n random variables and the expectation of g. Okay? So I want to express that as a sum over a martingale difference sequence. So, I mean, we're not using any properties of martingales here, so you don't have to know what they are. So if we define the initial sequence x1 through xi and worry about how the conditional expectation changes as we see the ith random variable, right? So this is our function g, and we consider how the expectation has increased. So vi is the increase in the expectation conditioned on seeing x1 through xi over what the conditional expectation was when we'd seen x1 through xi minus 1. Okay. When we condition on just the first I minus 1 of these guys. All right, then the random variable g minus its expectation is just the sum of these things, right? This is a telescoping sum. The first one, the expectation of g given nothing, well, that's this. And the last one, the expectation of g given x1 through xn, well, that's this. Right? So we can write it as a sum of these things, and now it's a sum of those guys that we want to bound the deviations of this thing. Let's say with high probability this sum is small. Okay, so I won't go through the steps, but the expectations of these things given the past are all 0. Okay, so this allows us to apply ideas of Hoefting, going back to Hoefting. And I'm going to go through the argument here because it's something that we will see later on. So, okay, so we can write the deviation between our random variable and its expectation as the sum of these differences between conditional expectations. And now here's a trick that pops up again and again, right? So the probability that this thing is bigger than that thing, well, let's take some monotone transformation of the two sides. Okay, in particular, the monotone transformation we're going to take is the exponential function with some positive constant s. Okay, so this is bigger than that precisely when e to the this is bigger than e to the that, or e to the s times this. Okay, and now this is something that we can bound using Markov's inequality. Okay, so does everybody know about Markov's inequality? If you do, nobody's admitting. So it's just saying, the expectation of some non-negative random variable, right, is at least as big as the probability that it's bigger than something divided by that times that something. Right, so we can get an upper bound on this probability in terms of an expectation of this thing times e to the minus st. Okay, this is called the Chernoff, the Chernoff bound. Right, this is an idea that's used in Chernoff bounds, and this trick appears in a lot of places. Well, this is an expectation of e to the s times some sum. Okay, that's a moment generating function. Right, we have a random variable here, and we're considering the expectation of e to the s times random variable. Okay, who's not met moment generating functions before? A few. Okay. This is modulo some sign change. This is a Laplace transform. So for the other electrical engineers among us, it's essentially the same as the Laplace transform. So what we're concerned with now, we can pull this e to the minus st out we're concerned just with controlling the moment generating function of this random variable. Okay, and we can express that as an expectation of this product. Our VIs are not independent. You know, the Hoeffding's inequality relies on independence of these things. We have something close to independence because of our, we have enough properties to make things work by conditioning appropriately. I won't go into the details of that, but you know, the whole game from now on is controlling the moment generating function of this random variable. Okay, and it turns out, conditioned on something appropriate. All right, so if we have a mean zero random variable that lies in a bounded range, all right, this is Hoeffding's inequality. Okay, Hoeffding first proved something of this form, maybe with a, I can't remember what, I think he got a different constant, and that was, no, actually Hoeffding got an it got the right constant. So you can show the moment generating function of a bounded random variable is bounded in terms of this e to the s squared kind of a quantity. Okay, and it's the bounded differences property that lets us argue that, you know, the appropriate random variables here are bounded. Okay, so now we get a bound on our moment generating function in terms of this variable s squared and in terms of the sum of the differences squared, and we just play with the variable s to come up with a bound on the probability that we get big deviations, and that's McDermott's inequality, right? That the probability of the deviation between g and its expectation being large is bounded by this decreasing exponential in t squared, right? So we get some sort of something that looks like a Gaussian tail, right? Provided that the random variable g has this bounded differences property. Okay, so that's where McDermott's inequality comes from. This idea of controlling the moment generating function of a bounded random variable is something that we'll meet again. Okay, so where are we? All right, so that's McDermott's inequality. Just to remind you, we're headed for this result, all right, that tells us that expectations are not much bigger than sample averages. And so far we've got that the supremum over the class of the deviations is close to the expectation of that thing, right? You know, a little bit extra because of that arises from McDermott's inequality. So now we just want to control the expectation of this thing, okay? All right, so, and this is where the Rademacher averages pop up in a very natural way. All right, so these things are very close to the Rademacher averages. All right, so I'm going to write a string of inequalities, and there's really nothing hard here. The expected maximal deviation between expectations and sample averages. Okay, I want to rewrite that deviation as an expectation. What have I done? Given the xi, what have I done? So I wanted to rewrite this as an expectation of a conditional expectation, and I've dropped one here. Anyway, so this should be that we can think of this expectation here as being g of xi prime minus the sample average of g. So I'm defining a new ghost sample, right? If we think of x1 through xn as having exactly the same distribution, being IID with the same distribution as x1 prime through xn prime, having the same distribution as x1 through xn, all right, then we can rewrite this difference as an expectation of a sample average of g of xi prime, right, minus, and this thing is also a sample average. Okay, so now over here I'm conditioning on the x1 through xn, right? Okay, so this is a notation. Given the xi means given x1 through xn. This is what I should have written. Right? And the expectation there is just worrying about the x1 prime through xn prime. So now I can take this expectation outside and I get an inequality. Right? But now I have something that looks just like g of xi prime minus g of xi. Okay, so what have I done to this point? I've replaced the expectation over g here with another sample average, right? An average over an independent sample, x1 prime through xn prime. Okay, so now this thing is quite symmetric, right? These have exactly the same distribution. They're independent, they have exactly the same distribution. Okay, so I could have as easily put g of xi prime minus g of xi, or I could have put g of xi minus g of xi prime. Right? Both of those things have exactly the same distribution. And so I can put a sigma I in here, right? For any fixed value of sigma I haven't changed things because this is just, right, the difference between g at some random, at least the distribution of this thing is unchanged. Right? Because it's just the difference between g at some random xi and g at some other random and independent xi. Okay, so I can throw these sigma i's in, the plus and minus ones, without changing anything here. But now this is looking a lot like Rademacher averages. All right, I've got a minus in there. Let's split this up into a sum of that one, sigma I g of xi, and this one, g of xi prime, and sigma I g of xi. And then I have, that I can write an inequality. It's no more than the sum of those two. Right? The expected supremum of the difference is no more than taking the supremum over this one and the supremum over that one, which is this. And that's just the Rademacher averages. Okay, so these things arise in quite a natural way. As soon as we make the observation that the expectation can be written as a sample average over these independent choices of x1 through xn, then the introduction of the Rademacher random variables changes nothing, has exactly the same distribution, and we get this, okay, we've introduced a constant factor 2 in here through this sort of an upper bound. All right, it turns out that there is a corresponding lower bound, right? That the expectation of the maximal deviations between these two is at least as big as some constant times the Rademacher averages. Okay, so all we're giving away in these inequalities is maybe a constant factor. Right? So in measuring, I don't state this explicitly in here, but in measuring maximal deviations between expectations and sample averages, the Rademacher averages capture that precisely within a constant factor. Okay, so there was one more thing that this tells us that gives us this result, right? The maximum over g of the deviation between expectation and sample averages is no more than this thing, right? Twice the expectation of the Rademacher averages plus a little bit that arises from the McDiarmid inequality. To see the second part, all we're doing down here is applying this for the class of loss functions. Okay, and so when we consider the expectation of g, we're worrying about the risk, right? The expected loss for some f. The sample average is the sample average of the loss. So all we really need to do to go from here to here is argue that the Rademacher averages for the class of loss functions is no bigger than the Rademacher averages for the original class, right? The class of plus minus 1 valued functions. Okay, so let's think for the discrete loss, these are the functions we're considering. The loss incurred by predicting f of x when the real outcome is y. Okay, so I can write the Rademacher average. This is just the definition, right? The expectation of the supremum of sigma, how much the loss vector lines up with sigma I. I'm going to write this discrete loss as the indicator of, right? So this is a function that takes value 1 when yi is not equal to f of xi and 0 otherwise. That's the definition of the loss, of the discrete loss, the 0, 1 loss. Okay, but I can rewrite this thing as a half of 1 minus yi times f of xi. Okay, because when yi is equal to f of xi, right, this thing is 0, just as it should be. When yi is different from f of xi, all right, this thing is minus 1, and we get 2 here divided by 2 is 1, just as it should be, right? So, you know, I haven't changed anything. I've just rewritten it as in a linear way. But now when it's linear, I can throw away this term, right? It doesn't depend on f. I just have an expectation of the sigma i's. Right there, plus minus 1, uniform. So the expectation is 0. That term disappears, and we get the expectation of the supremum of sigma I times yi times f of xi. All right? Well, if sigma I is uniform plus minus 1, what distribution does sigma I times yi have for any yi? It's exactly the same distribution, right? It's uniform plus minus 1. So this thing is just the Rademacher averages divided by 2. Okay? So in the case of discrete loss, the Rademacher averages of a loss class are equal to the Rademacher averages of the original class modulo this constant a half. All right, and that gives us, I don't know if I put it there, okay. And that gives us this result. Okay, so if we think of, this was the second part of the theorem before. If we think of this class of plus minus 1 valued functions, and we have discrete loss, the 0, 1 loss, then with probability that rapidly approaches 1, sorry, let me go back to the original theorem statement. So this part, the second part here, there's a slight refinement on that next slide. The second part here is what we've just proved, right? For a class of plus minus 1 value functions and the 0, 1 loss, with probability that rapidly approaches 1, every function has risk, not much more than empirical risk, plus Rademacher averages plus some little thing. Okay? And that's what we just showed, that the Rademacher averages of the discrete loss class are the same as the Rademacher averages of this class modulo the constant 2. Okay, one thing I guess I should point out just before we go on to that next theorem. This term here, the 1 over square root of n term, that's always small. All right? The Rademacher averages here, if you have a class that contains just the constant 1 and the constant minus 1 function, right, then the Rademacher averages are of order 1 over square root of n. Okay, so this is just like, equivalently, if you look at the definition of the Rademacher averages, which I've thrown away. So if this class contains the constant plus 1 and the constant minus 1, that's just like taking the absolute value here, right? The supremum over those plus or minus 1 guys is just the absolute value of the average of the sigma i's. Okay, well that's of order 1 over square root of n. Okay, because the variance grows linearly with n. So this term is, this second term is always dominated by the Rademacher averages, unless we have a particularly simple class. I should say for any fixed class it's dominated by the Rademacher averages. Okay, so a refinement of that result here is that, so same setup, we've got a class of plus minus 1 valued functions. Now we're saying we're considering just the minimizer of the empirical risk. Okay, so let's say we fix our class of functions f, maybe it's decision trees of a certain size. Then if we minimize the empirical risk over that class, so find the f, let's call it f hat, that makes the smallest number of mistakes on the sample. Then we can argue using that previous result that the risk of that minimizer, right, the probability that it makes a mistake, the expectation of this 0, 1 loss, is no more than the minimum over our class of functions of the risk. So this is the best we could hope for. We called this the approximation error before, right? Well, this is something like an approximation property of our class. This is the best we could hope for, given that we're choosing functions from that class, capital F, plus a penalty term of the same size as before, slightly different constant. All right, so the the picture of why this follows from the previous result is that we've shown that expectations and sample averages are close to each other uniformly across the class. All right, so the empirical minimizer has its expectation close to its sample average. The optimal function, the one that minimizes this quantity, the probability of misclassification, also has his expectation close to sample average. Right, if those two are uniformly close, then when we go from one to the other, we can't be too far away, right? The expectation can't be too far away from the expectation for the minimizer. The minimal expectation. The expectation of the empirical minimizer can't be much bigger than the minimizer of the expectation. Okay, so let's suppose that this infimum is realized at f star. This is the best function in our class, the one that minimizes the probability of misclassification, the risk. Then that function in particular has empirical risk close to risk, right? But its empirical risk is necessarily worse than the minimizer of the empirical risk, right? We were choosing f hat to minimize the sample average. Well, the optimal guy must have a bigger sample average that's at least as big, okay? But now we know that the sample average for this guy is close to his expectation. Okay, this is a single function. I don't even need to worry about Rademacher averages here, right? I know the deviations between these two through Hoeffding's inequality, say, is of order 1 over square root of n. All right, so that tells us that for the particular function f hat, we know from the previous result, its expectation is not much bigger than its sample average. Well, that sample average is not much bigger than the best expectation. Okay, so we get this result immediately. All right, so that's an example of an application of these Rademacher averages in getting bounds on the risk of a particular choice of function from our class. If we choose f hat, the function that minimizes the empirical risk, then its risk is close to the best we could have hoped for, given that we're choosing functions from f. How close? Well, it depends on the complexity of f as measured by these Rademacher averages. Okay, so once again, if we go back to think about the definition, the Rademacher averages tell us how much functions in the class line up with this random direction. All right, if they barely line up at all, right, then it's hard to fit to that noise. Right, it's hard to pick a function that fits to the noise vector. That's good. We'll get our risk close to the optimal risk. Right, the deviation term here is going to be small. If, on the other hand, we can always have these things lining up, then we might have a Rademacher averages like some constant, right, or as big as some constant as a function of n. Then the risk of the empirical minimizer, we have a rather poor guarantee, right? We could be some constant away from the best in the class in that case. Okay, so one other observation before I stop, that we can compute in the case of the 0-1 loss, we can compute Rademacher averages. Here's an interesting observation about the computation of these things. The Rademacher average is the maximum over the class of this thing. Well, I can write that as the negative of the minimum. All right, and then again using this observation that these are plus minus 1 and these f's are plus minus 1, right? I can rewrite this product in terms of a oh, I'm sorry, I'm not doing that just yet. So the minimum of this thing, I can throw in an extra 1 here and an extra 1 there, right? And then write this thing as the loss, right? Because remember, we saw this earlier that we can rewrite the loss of f of xi at some yi in terms of a linear expression of this kind. Okay, so you can see this by case-by-case analysis, thinking of sigma I, negative sigma I having the same sign as f of xi and a different sign. Okay, so what we get at the end is the Rademacher averages are equal to 1 minus the minimum over f, or I guess I should say infimum over f. Well, f is finite here. F takes only plus minus 1 value, so there are finitely many values of this thing. So the infimum is achieved 1 minus the minimum over f of an empirical risk kind of a quantity, right? We're looking at finding an f to minimize the empirical risk when we consider the y's as being these minus sigma i's, right? So we're trying to line up with the minus sigma i's. So computing the Rademacher averages is equivalent to minimizing empirical error on the randomly labeled data. We take all of our x1 through xn and throw in a random plus or minus 1 label and then try and optimize that. Okay, so later on we'll look at relationships between this notion of complexity, the Rademacher averages, and other notions. So the VC dimension is not something that depends on the probability distribution that generated the x's, but we can get upper bounds on the Rademacher averages in terms of the VC dimension. All right, so I'll stop there. I'm a little late, I'm sorry. Are there any questions? We should go directly to coffee.
So we'll have a